Hello, and thank you for joining us today. Our webinar today is on the MVX 7100 Workstation Low Volume Sample Introduction to ICP-MS. Our presenter today is Pete Winship. Okay, Pete, I'm going to go ahead and hand it over to you.
Thank you very much, and thank you to everybody for joining in on this webinar. Yes, my name's Pete Winship. I'm a product manager at Teledyne CETAC Technologies, and today I'm going to be discussing the MVX 7100 microliter workstation, which is one of the systems that I'm responsible for, and but particularly with respect to low volume sample introduction for ICP-MS, and that is from the point of view of overcoming low volume samples as a challenge, but also looking at them as a benefit or an advantage as well. So I'll move on in the, if I can. So just hold on a minute. I think we're having a technical issue there. So just bear with me 2 seconds. I can't seem to change slide. So if you can bear with us just 2 minutes, I can't seem to change the slide. Let's just see if we can change this.
Okay, I believe you should be able to just arrow over on your keyboard.
No, I can't. Left, right, it's not changing. Left, right, up and down, it's not changing. Ah. There we go. Excellent. Okay. Sorry. My apologies for that. Okay, I can carry on then. So the MVX 7100 microliter workstation system. This is the system that we're going to be under discussion today. So you'll get used to this image fairly quickly. So what I'll start with is just a quick agenda for this webinar. So I'll start with a basic introduction to this system, just go through essentially what it is, in a nutshell what it does. Then I'll be moving on to some background, why we developed the system, the reasons behind that. Then we'll move on to, essentially I'll do a hardware tour and the features and functions of the system. And then I'll move on to the idea of generating data. So generating data from limited sample from the point of view of an analytical limitation or a challenge, but also from the point of view of doing this for analytical advantage. And then I'll move on to some applications and examples just to give you a feel for where we've been using the system, what kind of analysis, what kind of applications have been successful with this system. So I'll start with an introduction to the MVX 7100 system. So what is it? What can this system do? Well, this is it's an advanced automation platform. It's an advanced auto sampler for ICP-MS, and it's geared up specifically for the introduction of low sample volumes for sample introduction for ICP-MS, but also what we might call suboptimal volumes, and I'll sort of make a distinction between the two as we go along. What we can do here with this system is we can introduce samples within the range of around about 5 microliters up to, in excess of 1.5 milliliters with this system to an ICP-MS instrument. I give an approximation here because you can move outside of those limits if you chose to, and I'll add some information to that as we go through. And then this system gives you complete control over the introduction flow rate that you'd want to work with. So, for example, we can go down to around about 5 microliters per minute, but then up into excess of 10 milliliters a minute, and well beyond if you wanted to, which is well beyond what you would need for ICP-MS sample analysis. Outside of that, so we're having trouble changing the slide again. There we go. What else are we looking at with this system? Well, this is a very configurable system in terms of both hardware and software. So this system can be as straightforward or as complex as the user likes, to basically set up the system so it's best suited to their application and their sample types. So we can include things like sample homogenization into the process of sample introduction. We can mix or add some turbulence to a sample immediately prior to it being sampled and taken up into an ICP nebulizer. We can incorporate temperature control. We can add septum piercing for samples if you want to be working with particular vials. You've got positional sampling as well, so you can pull your sample from a particular height in either a well plate well or a sample vial or tube if you want to be pulling from a certain point rather than going straight to the bottom. We can add additional modules, which I'll get to later, particular syringe pump modules. And we can also completely configure the rinsing processes for this. If you've got samples which can either contain really high concentrations of certain elements, or you contain elements of that will have particularly known memory effects. So I'll get into rinsing shortly. Right, so some background as to this system. Why did we develop it? Why bother at all with low volumes? Well, we were attending conferences and speaking to customers, speaking to colleagues, speaking to associates in different companies, and we were coming across the same question fairly regularly, actually, of what to do with certain samples where you've got either a small sample volume to work with, or a small low sample mass that you would then try and get into a low volume, where the elements that you're interested in, the analytes that you're interested in, are already present at trace levels. So what can you do with that? And that actually happens more often than you would think. That's certainly in certain applications that is more of a problem than not. So potential solutions to this. Well, the obvious first port of call is to take your sample and then try and dilute it, put it into a greater volume, so then you can work with it more easily. You can work with other types of automation. You don't have to worry about flow rates, and you can give you something better to work with. Now that's fine. That works for a lot of sample types, but unfortunately, if you certainly if you bring in higher dilution factors, you have the possibility of dropping of losing some analytes during the process. Some elements you might be interested in might fall below the level of the limited detection that you might have. So that might not be an option for some sample types. There exists, and there have done for a long time, some low flow rate nebulizers where you would use natural aspiration to take up a sample into an ICP. Those work very well for certain applications, but they do have some additional challenges as well for some sample matrix types. So for some sample matrix types, they might be too volatile. You might have some issues where you need to do matrix matching for standardizations. So it might not be appropriate for what you want to do. And then automation as well. There's a limited number of options in terms of automation in a non-metallic form for ICP-MS. These typically work with the low flow nebulizers. But they wouldn't cover a lot of the challenges that you might have in terms of low volumes. So this is not just a question that's been coming to us in recent years. There was a review paper released back in 2006 which discussed this as an issue, and there was a number of sample types proposed, whereby the sample volume or sample mass might be a challenge to what you're trying to do. And there, in this list, there was a number of sample types, and they're mostly from biological or clinical applications, but they all point to the same conclusion, which is that the available sample volume is a limiting factor in elemental analysis, or certainly can be. There's the question of available sample volume or sample mass. In that case, you might there just might not be any more sample available to you. You might not be able to take any more. There's also limitations in certain fields as well that you might have to consider. So an obvious one is blood analysis. So if you take a blood sample from an adult, you're most likely not going to have any limitations at all when it comes to sample volume, because you can take say, tens of milliliters from a person for analysis if you needed to, which you'd then dilute or you digest, and you'd have plenty to work with. But in most countries, there's legislations and restrictions in place on how much you can take from a child or an infant or a baby. So in that case, you would have a very limited amount of material to work with. So there's a number of reasons why you might not have very much to work with. Tissue biopsy is another good example. You might not have much actually out of a biopsy, and the sample might then need to be shared between multiple techniques. So it might not just be an ICP-MS analysis, it might be something else for chromatography or UV or infrared. So what I wanted to get into at this point was just the idea of what standard automation is. So our standard automation for ICP optical and ICP-MS systems is our 500 series automation. And you've got quite a nice range of sample volume to work within for that. Now, what I've got here is just along the bottom of the page, I've got what you might call a working sample volume range, going from one side of the screen to the other. Now, if you look at the 500 series automation that's here on the right-hand side of the screen, and there's a red arrow underneath, that's your what I'd consider probably a normal sample range to work within. You've got, you can have 50 milliliter tubes on there, and if you're doing water analysis, you'll have plenty of volume to work with. But for other sample types, you'll go down that scale. You'll go down into the single milliliter level, and at some point, you're going to reach this sort of grey area, where it's essentially, I sort of think of it as this area where you might have to compromise on the data that you're generating from your sample. If you get to it, you'll get to a certain point in terms of volume where you might be asking the question, do I have enough sample to get all of the analyte suite that I'm interested in, or all of the replicates? So there's this sort of grey area, and it's I've only sort of indicated really a sort of, that might be around about a milliliter, half a milliliter up to 2 milliliters, something like that, round about that area. So what I've done here next is I've added the MVX on the other side of the equation, where that system can then sort of take over. And essentially what you're doing here is when you move from one to the other, you don't have to compromise on that analyte suite. And that's something I'm going to get into later on as in this presentation. You can go down in that range, you can go further down, and you're not having to choose or to compromise on the data that you want to get out of it. So as I mentioned earlier, that volume range you might want to work with the MVX is somewhere around about 5 microliters up to about 1.5 milliliters. It depends on the kind of nebulizers you're working with and the kind of work that you want to do. But as a rule of thumb, that's what you can work within. And as I mentioned, you could actually go lower than 5 if you chose to. So the next step here is I'm going to give you a quick hardware tour of the instrumentation, and then I'll go through some features and functions as well. So this is what we have, the MVX system. As an auto sampler, it looks fairly complex, but I'm going to break this down and simplify it because it's a relatively straightforward piece of automation. So the first thing here is in the middle. The focal point is we've got an XYZ auto sampler. So this is the ASX 7100 system. It's one of our 7000 series auto samplers. and it's a very accurate, very precise autosampler for XYZ movement. So this autosampler will hit and allow you to take sample from a 384 well plate. It's that precise. On either side of the automation, you've got some modules, so additional modules. So in this case, we've got one on the left and one on the right. They could be either way round, depending on the kind of ICP-MS that you're working with. Or you could have them both on one side or the other if you chose. So in this case, I'm going to start with one of the modules here. This is the valve syringe module. Now this module is responsible for pulling your sample up from a sample vial and putting it onto a sample loop. So what we've got here is you've got, on that module, you've got a short syringe pump with a syringe on it. This is a 1.25 milliliter syringe. It's a PFA syringe there with PEEK fittings, and that marries up with a CTFE switching valve. So that pump is going to be responsible for pulling your sample out of a vial and onto your sample loop. That sample loop is mounted to a 6-port switching valve, which is above there. So the first thing you'll do is you'll take your sample and position it onto that loop. After that, the next thing that happens is you will move to the other module. So this is just a syringe pump module on the other side, and this has got hang on, wrong way, excuse me. So there's a syringe pump here, which is a longer syringe, a longer pump. So that is a 2.5 milliliter syringe there in this case. Again, another PFA with PEEK fittings syringe. Now this pump here is going to take the place of your peristaltic pump for sample introduction. So instead of using the peri pump, this syringe will push your sample off the sample loop and deliver it to your nebulizer and spray chamber for introduction. So the only thing that you're using your peristaltic pump for on your ICP-MS now is for draining the spray chamber. Now at the front, we've got numerous sample rack options, which I'll get into shortly, and then there's also temperature control as an option if that was something that you required for your work. And then on the left-hand side here, we have a dual rinse station as well, and that's all part of the flexible rinsing options that you've got. So I'll get to that as well shortly. Right, in fact, yes, get that shortly. Okay. So key features of the system. So I've mentioned a lot of this already. This is a syringe-driven autosampler with where you're using syringes for taking up your sample, so sample aliquoting, positioning it onto a sample loop, and then dispensing and introducing your sample to an ICP-MS nebulizer and spray chamber. For ICP-MS, obviously it's got to be metal-free, so it's got a metal-free flow path, and the materials in that flow path are can be quartz if you were to choose the quartz sample needle. Otherwise, the rest of it is PEEK, CTFE, or PFA. You've got the option to work with septum piercing if you chose, if you wanted to work with sealed vials, so like the VT54 HPLC style vials. So that's an option for you. I'll try and change slides again. Sorry, for some reason the technology doesn't want to play ball today. Sorry, everybody, just excuse me a moment while I try and work this out. Right, sorry about that. So moving on, so temperature control. Certainly for lower volumes or for samples where you've got a volatile sample matrix, or you've got samples where some of the analytes might be volatile themselves, such as boron or mercury, for example, you might need temperature control to control the temperature of your samples prior to introduction. So this is an option on the system. You can have, this is positioned underneath the sample racks or the well plates, and you can deliver anything between 4 degrees C and 40 degrees C. So you can drop down the temperature if you chose to minimize sample evaporation, if you've got a volatility issue, or if you've got very low volumes of sample. And then also you could raise the temperature as well. So if you've got samples whereby they might be more viscous, or there might be certain physical properties of the sample that need some heat to keep them, keep the solutions moving, to keep them in the kind of viscosity that you want, you might look to raise the temperature there. There's also the idea of using it as essentially incubation temperature for something like cell analysis, and that all of that is software controlled either in the ICP operating software or in our own software to run it. For racks, vials, tubes, etc. So we've got the option to work with HPLC style vials. So those are standard vials, so you could take your samples off a HPLC system, transfer them to this, and then move on to ICP analysis on the same samples. You can use microcentrifuge tubes, so if you need to spin down your samples and analyze supernatant, then you can do that with those kinds of tubes in a rack. And then you can work with well plates, so either 96 well plates or 384 well plates. They all have a standard footprint, so you can use pretty much any kind, and then you can work with different heights as well. So you could work with the short 96 well plates, where you've got a capacity of maybe 350 microliters per well, or you can work with the tall 44 millimeter height ones, which will give you about 2 milliliters of capacity to work with in each well. And then there's also other reagent standard bottles on the system as well. Right, nebulizer compatibility. This is something I'm going to come back along to later on in terms of the flow rate work. Now, the MVX system is compatible with most types. Now, I say that as a bit of a caveat because I've not met all types of this yet, but so far I've been able to work with every kind of nebulizer I've worked with the MVX system. So there's been no limitations up to date. So you can work with total consumption nebulizers, you can work with standard concentrics, or you could work with the kind of PFA wear, or you could work with nebulizers associated with more advanced nebulizer systems like desolvating nebulizer systems like our Iridus 2 or Iridus 3. So because we're defining what the flow rate is on the MVX, we're using the syringe to push the sample off the sample loop. Because we're defining that flow rate, we can work with pretty much anything in terms of a nebulizer. So we can go down to the total consumption flow rates of around about 5 to 7 microliters a minute, or you could work with something much higher. So something more, what is typically considered more normal, 0.5 milliliter a minute to 1 milliliter a minute. So we can work with pretty much anything. Like I said, so far I've not come across anything I haven't been able to use with this system. Right, so how does a typical sample introduction work? So I'm just going to take you through sort of the simple process here. It is a very simple process. So what we have here is, on the right, there's our automation, our ASX 7100 automation. And on the two modules in the middle, those are typically mounted either side, but you've got your syringe pump module on the left, and you've got your valve syringe module just next to it, on the right of it, in the middle. So what we've got here is, in the sample loading process, you've got two flows taking place at the same time. The first flow is the flow in blue here, where you've got a carrier solution which is driven from the syringe pump module that's sent through the 6-port switching valve, and it ends up at the nebulizer for your ICP-MS. Now that continually flows for each sample, so you tell it how much to push and at what flow rate to push it at. So that flow is always going to the ICP-MS. And then in the meantime, you've got the green flow. So at one end of that green flow, you've got your sample needle on the automation. and that flow goes via the 6-port switching valve, and at the other end you've got the short syringe. So the short syringe will pull your sample through the sample needle on the automation, and it will position that sample on the 6-port switching valve sample loop there in the middle. So once that's happened, once you've positioned your sample, the next step is the valve switches on that 6-port switching valve, and all of a sudden that sample is brought into the flow from the syringe pump module to the nebulizer for the ICP-MS. So that's now the green line. So your sample's in that flow, and you send your sample for introduction for measurement. And whilst that's happening, the other flow, the flow from the short syringe to the sample needle, that will backflush and clean the sample needle on the inside and the outside at the rinse station. Excuse me. So that's a simple sample introduction, and that's what will happen for each sample in a batch analysis. So you can be doing this small, low volumes, distinct volumes in a batch analysis setting rather than doing anything individually. Now the next slide, I'm not going to dwell on this so much, but there is an option to add additional modules to this. Like I said, you can keep this as simple or as complicated as you like, and basically match the automation up to the application that you're working on. And if you wanted to, you can add a number of other syringe pump modules to work with your system. So you can add a second syringe pump module for internal standard, perhaps. And that can be teed in, and then you have everything online in terms of internal standardization. You could also have another module for introducing another reagent into the process. So for example, in cell work, you could have another pump which is pushing buffer solution teed into the flow as well. So there's a number of options to add other modules if one were so inclined as part of their work. So that's where I'm going to leave that section of the presentation. Now I'm going to move on to data, which is probably where the greatest interest lies in terms of working with this system. So generating data from a limited amount of sample, what does that actually mean? Well, in this case, we're looking at using this system, the MVX system, to overcome the problem, or what might be a problem, of low volume. So you can use this system to overcome limits of introduction of sample of low mass or low volume, and then you can tailor what you're generating from your sample. So you can sort of work this backwards. And I'll give you a couple of examples as we go through this. So that's what I want you to think of in terms of this. Using the system to overcome the problem of low volume or limited mass, if you're going to do a digest, and then looking at the best way to generate your data. So I'm going to move on to a question next, and that is, and this certainly happened to me before I worked for CETAC and Teledyne. Working in a laboratory environment, and somebody would come into the lab and sort of hand me a vial, and this happens. This happens a lot. Somebody hands an analyst a vial and says, "What can you do with this?" They've got a sample. They'd like to get some data from it, and the question goes to the person running the instrumentation. What can you do with that? And I think possibly this might sound a bit like semantics, but that's possibly the wrong question. I think that the better question is this one, which is, what do I want from this volume? Not focusing on the volume as such, but what do I want from the process? What do I want to get out of it? So I think you go from that and you start questioning, you start picking it apart, and you look at this, and really this is a question of measurement time. So how much measurement time can I get from a sample to generate data from? So that's where I would start with this kind of discussion. So what do I want to get from my sample? What size of analyte suite do I want? Do I want just 5 elements, 5 isotopes? Do I want 50 elements and 50 isotopes? How big is that analyte suite going to be? For quadrupole-based ICP-MS, as a general rule of thumb, the larger the analyte suite, the longer the measurement time that you need. How many replicates do I want? Do I want 3 replicate measurements when I do this? Do I want 4? Do I want 5? Again, that affects the measurement time. For quadrupole-based ICP-MS, are there gas modes to consider for collision cell or reaction cell analysis? And then the question, after I've done my analysis, do I want to repeat it? Do I want to do a second analysis to compare the data? Do I want to do a third analysis? All of this then affects the measurement time. So that's where, with the MVX system, I think that's where we need to start. The idea of what do I want rather than what can I do? So starting with that point, that then takes you into the idea of you assess these and you look at measurement time. And then we move on to the idea of essentially you've got a three-component equation, factoring in your sample volume, the introduction flow rate, and the measurement time that you want from your analysis. So in this case, if somebody hands an analytical chemist, an analyst, somebody working in a laboratory, a sample vial with a certain volume in it, that's one of our variables ticked off. We know that. If we know how much measurement time we want to get out of this, what our analyte suite is, etc., we know that as well. So the only question left is what introduction flow rate do we need to be able to allow us to get the measurement time that we want. So it's working backwards. So from that, I've got an example for you. So this is a very, very simple example, really. This is something that will appeal to most people in an ICP-MS lab. This is just a multi-element standard, a 1 ppb multi-element standard used for tuning, for example. And this has been introduced via the MVX through a typical 400 microliter a minute concentric nebulizer. Nothing particularly special about it, a sort of a standard industry nebulizer. Now, I've taken 100 microliters of this solution. 100 microliters, some people, is a lot of solution to work with. To other people, it's a tiny amount. So what I've done to start off with, just to give you a frame of reference, is that 100 microliters was introduced to an ICP-MS at 200 microliters per minute with the MVX system. The syringe on the MVX system has pushed that through to the nebulizer, introduced it at 200 microliters a minute. And that's given us about 21 seconds of stable measurement time. So for some analysis, that might be plenty. For some analyte suites, some number of replicates, that might be plenty. That might be fine. That might be nowhere near enough. You might need twice that, 3 times that. So what happens if you just start playing with the introduction flow rates? So if we do the same again, 100 microliters, introduce it at 50 microliters a minute less, at 150 microliters a minute. All of a sudden, we've still got stable measurement, but we've got 10 seconds more. Now, the latest generation, ICP-MS instrumentation development has been moving at a phenomenal rate over the last 30 years. And with every new generation, the sensitivity has been getting better and better. So to go down in terms of flow rate, you sacrifice a bit of sensitivity, but with modern ICP-MS, that matters less. So at lower flow rates, you can stretch out your sample. You can make the most of it. You can get more from it, more data, more replicates. You can get more out of it whilst not sacrificing too much in terms of sensitivity. So I've given you an example of just dropping it by 50 microliters a minute. What happens if we take that further? So again, the same example. We drop it down by another 50 microliters a minute, and all of a sudden we're up to 48 seconds, just at 100 microliters a minute there. Again, the same sample, the same multi-element standard solution via the same standard nebulizer. What happens if we take it further? Drop it to 75 microliters a minute, all of a sudden we're over a minute. So there's been no change to the nebulizer through this either, which would give us even more benefit. And then the last example I'll give, what happens just a bit further. So to 50 microliters a minute, now we're over a minute and a half, just from 100 microliters of sample. So, and this isn't the end of the story either. You could keep going. You could keep going all the way down to total consumption, introduction flow rates, and you can get so much more out of it. So our DS5 nebulizer that we offer typically runs with the MVX best at 7 microliters a minute. So if you imagine running your 100 microliters of sample, 7 microliters a minute, that would give you a considerable amount of measurement time to work with. So that's what I'd like you to leave with in terms of this, that low volumes really aren't that much of a challenge as they might have been previously when you're looking at it from this point of view. So before I move on to applications and examples, one of the other things I wanted to note to you is that we originally developed this automation system to overcome a problem, the problem of low volume, the challenge of those kinds of sample types. What we've also found is that there's actually, as well as using it as a means of overcoming a challenge, there's actually a benefit, there's actually advantages to working with low volumes and low flow rates for a lot of application types. And this is something that we hadn't foreseen at the outset, really, but have come to understand as we've gone forward. So actively going to lower volume and lower flow rates, it would appear that there are benefits in terms of greater processing power from the plasma, less disturbance to the plasma as your sample's going through. And we've certainly seen for certain sample types improvements in limits of detection. So a good example for you is in a xylene-based matrix for some oils analysis. On a like-for-like comparison between working with and without essentially the MVX system, but working with the same samples. If you go with low flow rate and low volume, we've seen an improvement in detection limit by 5x, so five-fold improvement in detection just with some basic testing to go to low volume. We've seen improvement in batch robustness, working with some more challenging sample matrices. We've got some ongoing projects on that. And then there's also the idea of, if you're going to low volume, then you're reducing the amount of waste that you're generating, you're improving some of your costs. And there's also safety improvements as well in some cases, so particularly thinking of the nuclear industry. So there's a number of advantages there. So next, to round off the presentation, really, I'm going to go through some applications and examples that we've certainly seen. We've been through this over the recent months and years with this system. So I'll walk you through some of these. Some of them are fairly obvious, others are some that we hadn't foreseen. But to start off with, before getting into applications, I'm just going to have a sort of a recap on why use the system. So we use the system for low or suboptimal sample volumes. So your low volumes, you might consider those to be hundreds of microliters of sample, tens of microliters of sample. That might be considered low. Your suboptimal sample volume might be considered something just in that grey area that I noted before, that area of potential compromise. So I'm not saying it's always compromised, but that area where you might have to really think hard about what you want to get from your sample if you're using a different kind of automation. You've also, so that overcomes issues of limited sample availability. You might be working with something a bit more precious or costly. So if it's a sample where you consider, well, I've only got one shot at this, with the MVX system, that might give you 2 or 3 turns at the same kind of sample. Something costly, some industries, some research and development, you're going to be working with new things, expensive reagents, that kind of thing. The MVX can reduce the volumes of things that you're working with and allow you to reduce some of those costs. And then also there's the idea of repeat analysis on limited volume. As I just mentioned just shortly a while ago, intentional reduction of sample volume gives you some other benefits as well. The reduction of the use of expensive reagents, reduction in waste. Also, if you're working with things like organic solvents, if you're putting less organic solvent into an ICP-MS via the MVX, then essentially you're putting less material, less carbon through the system, which can be deposited on the cones. So you're also sort of saving parts of the instrument, like the cones, the torch, from exposure to the sample matrix. So there's also some other benefits that we've seen as well, some other reasons to use the system. So There's no peristaltic pump tubing associated with sample introduction in this case. Now, peristaltic pump tubing is great for a lot of applications, but it doesn't stand up very well to certain reagents, particularly organic solvents. So there's some issues if you want to be working with a concentrated organic solvent, you might have some issues with that kind of tubing. Whereas if you're using PFA tubing or other kind of harder plastic tubing, then you're not going to have that kind of issue. So particularly with concentrated organic solvents. So we've certainly seen benefits in moving to the MVX with that kind of tubing, those kinds of plastics, those kinds of materials, with NMP, the semiconductor solvent, and things like xylene. Septum piercing, I've mentioned a fair bit through the presentation as well. The idea of being able to protect your sample, having it protected in a particular vial in a finite volume for in the event that you've got volatile organic matrices or volatile sample types. So in terms of applications, one of the areas that we have seen a lot of interest for the MVX system is in clinical and biological applications. This is probably where you're more likely to come across some of these lower volumes or lower masses to be able to work with. So the kinds of samples in biological and clinical applications that we've seen to date, bloods and serums, as I mentioned before. In a lot of cases, volume is not an issue, but there are those legal limits, those legislations in place in certain cases. Urines is another one. Tissue biopsies, you might be looking at limited material. That material might need to be shared or split between different analyses. Another one, a new one that we've just come across fairly recently that we're going to be working on is cerebrospinal fluid. Again, that's the kind of sample that you can't take very much of. So there's an interest in that we're currently looking at. And then single cell analysis is an area of real growth at the moment that's being explored. And we've got a launch this year with a new glassware interface which will marry up with the MVX system to cover single cell work. Just a specific example, just to let you sort of walk you through another example in clinical or biological. We have a customer at Public Health England in the UK who has been working on blood spot samples with the MVX system and ICP-MS. Now, excuse me, in the UK and in most parts of the world, there is what we call the heel prick test, where blood spot samples are taken from newborn babies after they're a few days old, and then those blood spots are taken as via the heel. So you get a prick on the heel. Those bloods are then put onto a test card, which is shown on the bottom right-hand side of the screen. And those test cards are sent, I believe it's for vitamin analysis. It's nothing to do with ICP anyway. So this customer that we have in the UK at Public Health England has actually been looking at these test cards that are available because there are excess sample on the cards. There's more sample on there in those spots than there needs to be for its original intention. So he's been looking at these cards as a means of using them to establish trace element concentration of these bloods after the fact. So he's been taking a punch from these cards that contain the bloods, and he's been digesting these punches in 96 well plates, and he'll end up with about 0.5 milliliter of sample volume. And to get the most out of the analysis, he's been using the MVX to do this. So just a shot here. So you've got on the left-hand side there, those are his punches in a 96 well plate, and then he's been doing his analysis there on the right. Now, geological applications. This is an area that we've seen a lot of benefit of the MVX system in. And again, this is not something that we really originally considered at the outset. Now, multi-collector analysis, whereby you're looking at isotope ratio, there's a massive benefit here in using the MVX system and going towards low volumes and low introduction flow rate for that kind of work. Now, some of the key variables for this kind of work is the analytical accuracy and precision of what you're doing, particularly in things like geochronology and geoaging. So this is data which has come from the British Geological Survey in the UK. They have an MVX system in their lab, and they've been looking at the kind of precision of measurement that they can get using the MVX system for natural uranium. So in this case, they've looked at 2 nanograms of uranium, and they've compared what the MVX is capable of, with what is considered normal in conventional sample introduction. So conventional sample introduction in this case is typically a self-aspirating nebulizer with a piece of automation with it. And you can see there the data for that conventional approach is in the red crosses there. So you can see there's actually quite a spread of those data points against the precision for 2 relative standard error on natural uranium 235 to 238. Now, that's what we get for conventional, but if you move to the MVX systems, so that's the data in the blue crosses there, you get a much tighter grouping of your data points, and that is a greater than 50% improvement in the precision of analysis, and it's considerably more repeatable as well. Now, that might not sound like a lot to sort of non-geochemists, people who don't use multi-collector, but that's actually quite a big leap. And it's also, the MVX system has allowed that accuracy, precision, repeatability, with actually using a lot less sample and doing it a lot faster as well. So that's an area that we're currently exploring. There's a real benefit there to geochronology in multi-collector work. Outside of that, but staying in geology, so sorry, this is essentially a conclusion summary to what I've just said there. Outside of multi-collector work and geochronology, for geological study, you might be looking at things like samples where you might have growth bands. You might be looking at things like shells or speleothems or that kind of analysis, whereby you're looking at spatial resolution of a sample. That might be your overall interest. So in some of those sample types, you might be looking at trying to remove a certain mass of sample, a certain mass of material from a growth band, and then trying to get that into solution. So you start off with a very minimal amount of sample mass, and then trying to do a digestion on that, whilst not trying to lose any of the elements that you're interested in, or making sure that those elements don't drop below the limit of detection. So what you can do here is you can do a micro digestion. You can keep everything very small. You can micro drill out the material that you want. You can get it into a small volume, digest it, and then put it onto the MVX system, and then do your analysis that way. So just to give you an example here, this is more work from the British Geological Survey in conjunction with the University of Bangor in the UK. This is data from a whelk shell, which is part of a global warming study. And the study here has been to look at the difference in terms of ion composition in these different growth bands as this shell has grown. And over time, the immediate environmental conditions have changed around that shell. And what you can see here is that you're looking at a distance here on the x-axis of this graph here. So it's essentially, we're looking at distance as a representation of time. So as the shell has grown in the earlier part of its life, there's been a greater amount of iron there, and then as it's grown older, there's the amount of iron reduces. Now that data has been correlated into global warming studies, but all of this has been made possible by the ability to work with a low mass of sample and getting that into a low volume, which you can then introduce to an ICP at the right flow rate. So we've actually been exploring a very wide range of applications. So, we've gone from our clinical and biological, we've moved into the geological world. We've also seen very benefits in working with organic-based solvents and petrochemical work. So this is the next bit I'm going to go into. I've mentioned before on the potential benefits of working with low volume, low flow rate in terms of organic solvents, and essentially this is a summary of that. We're looking at when you go into low volume, low flow rate, you're putting less carbon into a plasma, you're depositing less material of that kind, less carbon onto sample cones. You're looking at being able to protect your tubing as you go through this. There's no peristaltic pump tubing that you've got to worry about in terms of it being degraded. There's also, if you're working with organic solvents, then temperature control, septum piercing will be very beneficial in terms of minimizing any loss to evaporation, and it improves signal stability as well. Right, so essentially a summary of essentially what I've just said. So working with low volume, less deposition on your cones, protect your pump tubing, sealed vials, keeping your sample in isolated, and temperature control, very beneficial, and having less matrix going into your plasma at any one time. Some examples for you. The NMP solvents, typically used in the semiconductor industry, it quite happily melts peristaltic pump tubing. It really is very good at doing that. But going through the right plastics, the right materials on the MVX system, that's not an issue at all, and you can introduce that into an ICP in its concentrated form. So there's no need to dilute it, which I have seen in a number of application notes. There's no need to do that at all. And again, working with low volumes and low flow rates, you are potentially improving your limits of detection there, whilst not having to worry about what the solvent, the sampled organic solvent is going to do to your system. Xylene-based matrices. Xylene is a common matrix for petrochemicals, crude oils, that kind of thing, biodiesels. Xylene, again, doesn't like peristaltic pump tubing, and if you're pumping a lot of that kind of matrix into an ICP plasma, then you're going to have issues with signal suppression, etc. But again, what we've seen is if you move intentionally to low volume and low flow rate, you maintain the sensitivity that you had with your system while not having a greater impact on your analysis from the sample matrix. And then things like there's a new ASTM method, 8110-17, which is ICP-MS analysis on distillate products in the petrochemical industry. The MVX is an ideal fit for that ASTM method. So some additional applications. Again, we've been exploring all over. So we've gone from the clinical and the biological through geological, through organic solvents and more industrial work, and then we arrive at things like the pharmaceutical industry and the nuclear industry. I've already mentioned that working with low volumes can be beneficial for pharmaceutical industry in terms of R&D. If you're working with something expensive, new expensive formulations, or something that you've only got a limited quantity of, a limited amount of, the MVX can actually allow you to get more out of less. And then there's also things like the DMSO solvent, a common solvent in the pharmaceutical industry, which has a solidification point of about 17-18 degrees C, so quite close to room temperature. So if you've got a cool day in your lab, you might end up with a problem with your DMSO matrix. So having the DMSO-based samples being analyzed through the MVX system, you'll first of all get a benefit with being able to work with things like temperature control, but again as well, with it being an organic solvent, low volume, low flow rate, you'll be able to realize some improvements in limits of detection. The nuclear industry, we've had a system go out into the nuclear industry, and it's been very interesting to see that running. Again, you've got an example here of being able to work with lower sample volumes from the point of view of improving costs and also improving safety. The idea of being able to put less of a sample into an ICP system, whereby you're not going to have as much waste come out of your spray chamber. You don't have to. That's less waste to consider for disposal. So you're looking at an improvement in safety in terms of handling, and also a reduction in costs in terms of disposal. So there's a number of benefits in terms of the nuclear industry that we're looking at with the MVX system. So we're exploring all the time new ideas new approaches to looking at low volume, low introduction flow rate, and how beneficial this is to ICP-MS analysis across the board. So that's where I'm going to leave it for today. So I want to thank everybody for attending and joining in this webinar. Please feel free to forward me any questions. My email address is below there. I think that's the best approach to this, because we could spend a long time discussing these things. So I think that's the best thing to do. So please feel free to email me any questions. I've also added, sort of as the next slide here, this is our webinar schedule for the rest of the year. You can access this on our website. I'll be running another webinar on the MVX 7100 system, specifically on single cell analysis towards the end of May, so that's May 30th. So that's to match up with what's coming in terms of our new glassware. We've also got another webinar on the SDX system later in the year in Iridis 3 and AS Express. So please come and join our webinars through the rest of the year. And thank you again for joining the webinar today, and I look forward to hearing from you.